Hello and welcome to this reboot of 3 Paper Thursday, the first one in almost 8 years. And today we're going to be talking about sanitizers and mitigators. That is the different ways in which you can either sanitize a program to debug it and detect the existence of programmer errors in low-level languages such as C and C++, or just mitigate them, stop them from being useful to do an attack on a program or system. There are lots of different ways in which you can insert these sorts of mitigations or sanitizers into programs, and we're going to look at 3 very different strategies today. The first will be using a binary translator to insert into existing programs. The second will be the variety of techniques that you can use to insert this kind of instrumentation using the compiler. And then the third will be my own technique, which is a hardware accelerator for the purpose that is programmable. Okay, so the first paper we're going to be looking at is called RetroWrite, and that was published will be published in S&P this year. The way this works is that it uses rewriting techniques on closed source binaries to instrument them to detect various forms of vulnerability. To sanitize them against the many types of programmer error that can occur. It argues that doing this in the binary is a lot better than doing it in the compiler, because this means that you can target any binary. Anything that you're running on your machine that you don't necessarily trust, you can run all sorts of fancy instrumentation analyses over it. So the previous state of the art here are things like QEMU and Valgrind, which are dynamic binary translators. They change the program at runtime to instrument it and work out whether it's doing anything wrong, but these are very, very slow. This paper argues you can do a lot better than that if you do this changing of the program statically before you run it. The only problem there is that this can affect the safety of the analyses that you're doing. You can cause valid programs to crash because you can the reason this can cause valid programs to crash is because in most ISAs, in most architectures, you don't know whether what you're reading in is an integer or a pointer. And so you don't know where your control flow is going, which means when you want to change that control flow, insert new instructions to instrument a program, you may break it completely by misidentifying the two. However, this argues that this kind of analysis is a lot easier on a specific subset of applications, which are 64-bit position-independent executables, where you use a redirection table to look up everything, and that helps you for this because it allows you to redirect through that table and identify what you need to. As a proof of concept, RetroWrite implements a fuzzer using their technique, using their static technique to inject random inputs and see if it can cause a crash and therefore break the program, and also an address sanitizer-like strategy where it instruments every load and store to see whether those are, for example, out-of-bounds accesses. It achieves similar levels of coverage to the compile time counterparts and is significantly faster than the aforementioned QEMU or Valgrind. Okay, and that brings us on to the systematization of knowledge paper then, Sanitizing for Security, which was in S&P last year. This is a compilation of all of the various analysis techniques that are in the literature, most of them implemented rather than in binary translation like the last paper, typically in the compiler. This paper makes a distinction between sanitizers that look for the existence of bugs and mitigators that try and hide them, where sanitizers can have slightly higher false positive rates, whereas mitigators can't have any false positives. And sanitizers are typically used in debug rather than deployment, therefore you can have slightly higher performance overheads, whereas a mitigator you can't really go over 5% before the thing will be switched off and therefore won't be deployed in the real world. The paper looks at the variety of attacks and mitigation strategies against these, both things that are production deployable, like LLVM control flow integrity, and things that are used in debug, like address sanitizer, which we've already talked about. In terms of future research, it discusses the three different directions that will be useful. The first is, how can we compose sanitizers? How can we run multiple different sanitizers at the same time so that they don't conflict with each other? And also, only the most relevant one detects the bug rather than it being passed between all of them and generating lots of useless error messages. The second is, how can we improve the performance of sanitizers using hardware features to accelerate where appropriate? And then finally, how can we design sanitizers to deal with low-level system code like the operating system kernel or things that are running bare bones without anything underneath? That brings us on to my paper, The Guardian Council, which deals with the second of those issues, hardware support. Instead of instrumenting the binary or adding compile time instrumentation, the Guardian Council, which is our new architecture published at ASPLOS to offload this into hardware, instead instruments in the hardware. So what we have is a hardware debug channel that analyzes the instructions of a program that is being executed and sends that off to a programmable analysis engine able to deal with working out whether that instruction is part of an attack, for example. The key to having a high-performance analysis engine that is programmable, the trick behind the Guardian Council, is many core architectures. What you have is your conventional CPU core surrounded by a sea of tiny microcontroller-sized cores, about 1,000th of the size and 1,000 times more efficient than your regular core. And you run lots of different analysis tasks on that in parallel, and you parallelize your analysis tasks across these many different cores. That means that you don't have to sacrifice the programmability, and you can still have very high performance and low overheads. We offload a variety of different strategies onto this, including LLVM CFI based techniques and an address sanitizer like policy, and you can do all of these in very low overheads. There's a full talk on this that I did virtually for ASPLOS a couple of weeks ago. The link will be in the text below. Okay, so then what about future work then? The Guardian Council's hardware architecture hasn't yet been deployed on real systems. There is significant value in being able to deploy low overhead pure software strategies, especially to existing code, as in the first paper Retrowrite. Can the overheads, coverage and analysis challenges of that sort of work be solved maybe using a hybrid static dynamic scheme that we've seen for parallelizers like Janus? More generally, the algorithms used for debug sanitization are typically plagued by false positives and false negatives. Any work to improve those for any of the various sanitizers in the literature would be of significant benefit to real applications. Runtime mitigators need overheads as low as possible if they're to actually be deployed, and aren't allowed any false positives whatsoever if they're going to be used on real-world application code. So if we can generate new ones for these for any kind of attack, there is real value there for all real-world applications that are written in low-level languages. Okay, so that is a very brief introduction to the three papers on sanitizers and mitigators. By no means the only work in the field. I'd be very interested to hear in the comments below what your favorite papers are in this area. Thank you very much for listening. I hope this was a fun video. Hopefully see you again soon for other people's 3 Paper Thursdays.